The volumetric efficiency depends on many factors. In fact, I will go over these factors when I talk about intake system in the coming lecture. And mostly the dominant factors which decide the volumetric efficiency of a spark ignition engine is more or less the valve timing, throttle position, and of course the airflow dynamics, fluid dynamics of the airflow in the intake system. Now, as we all know, this in petrol engines, we suck air into the engine, and at some stage in the intake system, we introduce fuel. To decide how much of fuel is to be introduced, or the amount of fuel to be introduced, we have to have a measuring system which measures the amount of air goes into the system. And then for a complete combustion, there is something called stoichiometric air-fuel ratio. I'm sure you are familiar with this. Basically, it comes from the chemical equation of the combustion. So the stoichiometric air-fuel ratio is more or less 14.7 for petrol. And when 14.7 units of air goes into the engine or sucked into the intake system, we'll have to introduce 1 unit of fuel. So there has to be a measuring system to make sure that correct proportion of fuel is introduced. For that, in old engines and still in small engines like motor bicycles, lawn mowers, and things like that, there's a fantastic mechanical gadget which was invented about 150 years ago, which was called carburetor. And the carburetor is geometrically designed to make sure the air-fuel ratio is approximately 14.7 air-fuel ratio could be maintained. And we have a choke with upstream, and then at the downstream of the carburetor, the throttle valve is fixed, and the carburetor is more or less a diverging and converging tube, as you can see here. And as the air flows through this carburetor, amount of fuel is introduced due to the pressure difference between this point and the pressure, atmospheric pressure, that is maintained somewhere here. So the pressure difference over here and here allows the fuel flow, and the pressure difference, you'll have to make sure that you'll have to generate the right pressure difference to introduce the right amount of fuel. This so basically this is the throttle valve, which is directly connected to the accelerator, and the opening of this one will decide how much of air goes through this one. And this convergent divergent tube, in other words, the carburetor operates based on the Bernoulli's principle. That means you can neglect the head in this case, H rho G, because the pressure head, because there's no significant height difference. So the pressure and the velocity would decide the net pressure. So so that means that when the pressure, the velocity increases, to make sure that this Bernoulli's principle is obeyed by the gases as they flow, air impact. When the pressure is increased, the velocity has to go down. In other words, when the velocity is increased, the pressure has to go down. So this reduction of area over here will increase the volume, the velocity, as the volume flow rate is constant. So the velocity increases as the area reduces. Therefore, the pressure drops as a result of increase of velocity. So that pressure drop led this fuel to come through. So the geometric design of these passages and other components enables this the magic ratio of 14.7 is maintained. So that is basically the operation of a carburetor. And in the upstream of the carburetor, there is another gadget connected, which is called the choke. So the choke, I'm sure you are familiar with this term choke. When you start a bicycle, for example, in the morning, you'll have to pull the choke first and start. Otherwise, it's difficult to get the bicycle started. What we want is, if you have more fuel in the mixture, it will be easy for us to burn it. But it's not a complete combustion. But to start the combustion, if you have more fuel, it will be easy. So particularly during the cold start, we want more fuel in the mixture than air. That means air fuel ratio, the identical air fuel ratio, the stoichiometric air fuel ratio is about 14.7. And if you can maintain it up to 12, for example, more fuel, less air, then the start would be easy. So that is what we are going to do with this closing of this choke. We can, of course, the amount of air coming in is less, but the velocity of this is more. So that means we can increase the velocity further over here, and then the reduce pressure drastically at this point, so that more fuel will flow in. So you don't need a lot of air to start the engine, because you are not running you are not driving any load at the start. You just the vehicle is in the neutral gear, and you need power to overcome friction. Therefore, you don't need a lot of power to be produced. Therefore, you don't want a lot of air coming in, but small amount of air is enough, but more fuel is mixed with it, so that start is easy, particularly in the cold start. When the engine is hot, of course, that high temperature also enables burning. Accordingly, you don't need to pull the choke when you start the engine under hot conditions. But under cold conditions, the temperature is less. Therefore, the start of combustion is difficult. Therefore, we try to burn more fuel at the start. So that is with the carburetor, but all these chokes and things like that, you hardly find, you don't find in modern engines with electronic fuel injection systems, because these things can be decided within the microcontroller, depending upon the measurement of temperature and things like that. Of course, we find this magic device called carburetor in small size engines, still motorbicycles, lawn movers, and things like that. We find carburetors, but in modern day automobile engines, particularly the mid to large size engines, we hardly find these carburetors. Instead, what we have is EFI systems. Now, if it is a multi-cylinder engine, 4-cylinder, 6-cylinder, 8-cylinder engine with carburetor, then what we have is this engine manifold. So the engine manifold branches out this airflow into different engines, different pistons, different combustion chambers, as you can see here. So this gadget, this structural element is called the intake manifold. So you have only one carburetor and one place to suck air in, one air filter, but the things are branched out to different cylinders, as you can see here. So that is the way the multi-cylinder engines are operated with carburetor. But of course, the modern day engines, we hardly find carburetors, at least mid-size to large-size engines. Instead, what we have is a fuel injector, which injects the right amount of fuel into the intake system, or sometimes directly into the engine if it is a direct injection engine. So in that case, there is no carburetor, only a throttle valve is there. But then again, we'll have to make the measurement correctly to make sure that the right air fuel ratio is maintained. For that, there are series of sensors connected to it: air pressure sensor, air temperature sensor, throttle position sensor, etc. So these sensors are connected. Usually this the throttle valve is operated using a DC motor connected to the accelerator through a electrical connection. The throttle position sensor is more or less a potentiometer or encoder. And so this engine control unit measures the airflow rate, keep track of the airflow rate, and introduce the right amount of fuel into the intake system. So that is the operation of electronic fuel injection, and there is an algorithm running here. So if it is a cold start condition, the system will give you more fuel. We call rich mixture, rich in fuel. So it will produce a rich mixture to enable a cold start, so that we don't need any choke or anything like that. The system itself will decide based on its own measurements. And of course, in most modern engines produced over the last couple of years at least, they use this technology called gasoline direct fuel injection, where the fuel is directly injected into the combustion chamber, as you can see here, during the intake stroke, of course. But in other generations, the engines produced before 2018 or 2017, if it is a multi-cylinder engine, multi-point fuel injection technology is used. So in fact, there are 3 generations of electronic fuel injection. The first generation is the throttle body fuel injection. That is exactly similar to the carburetor action. Instead of a carburetor, there is a fuel injector, but the injector is fixed at the place where the carburetor was. So that the place where the carburetor was placed in the old engines, the carburetor is removed, fuel injector is connected. So the geometry is the same. Before the throttle valve, you inject fuel, and the fuel is branched out to these different engine compartments or different cylinders, as in the case of carburetor. So only difference is there is no carburetor, but there is a fuel injector. So this system, of course, the problem is now the gasoline combustion is called pre-mix combustion. That means to get the maximum combustion efficiency of gasoline, we have to have a homogeneous air-fuel mixture before burning. So before burning, we'll have to create a homogeneous air-fuel mixture. Air and fuel is very well mixed across. So for that, to enable this mixing, you introduce this fuel earlier, so that the fuel has enough time to mix. So the fluid dynamics created, the flow patterns created in this intake manifold enables this mixing, and also during the intake stroke, the flow patterns within the cylinder as the piston goes down creates some fluid mechanics phenomena which enables thorough mixing. So the reason why in the first generation EFI systems the fuel is introduced earlier is to enable this very well mixing. And the next generation, the multi-point fuel injection systems were developed, where the fuel is injected quite close to the cylinders, but again into the intake system. So the flow dynamics of intake, flow dynamics of inlet stroke within the cylinder has been improved based using various technologies, so that after some time of these throttle body injection systems, you did not want a long time for this mixing due to the improved fluid mechanics phenomena within the cylinders during the intake. Therefore, this injector was moved up close to this cylinders. The advantage of doing so is basically when you introduce fuel over here, then there will be some fuel deposition on the walls of the intake system and the throttle valve and things like that. Therefore, certain amount of fuel goes to waste. So you can't make the full use of the fuel due to these losses, due to the deposition at different points, the evaporation and various other things. Therefore, the people wanted to move this close to the cylinder. So the next generation, the multi-point fuel injection systems were developed. And very recently, gasoline direct injection technology was developed, Then there is no fuel introduced into the intake system or the intake manifold. The fuel is directly injected into the combustion chamber or the intake cylinder inside the cylinder at the beginning of the intake stroke. So again, the main challenge for this direct injection engine is creating homogeneous airfoil mixture, but the fluid flow phenomena, the flow dynamics are improved such that within a very short time, this mixing could take place. Accordingly, the direct injection became possible. So these are the three generations of fuel injection systems. First generation throttle body fuel injection systems, then the multi-point fuel injection system, and then came the direct gasoline injection system. So the most modern engines which are produced from 2018 or so, particularly in developed countries like Japan, USA, Germany, and those places, the engines, diesel engines are direct injection engines. So these things we'll discuss later, but just for your information, I put this slide. So there are many sensors nowadays connected in engines. There are so many measurements we make, and there is a kind of intelligent engine control algorithms in place in the engine control unit to take care of the operation of the engines. These are learning algorithms. So there are so many advanced technologies are used in modern engines rather than the engines that are used 30 years ago. So there's a huge development of engine technology with the introduction of microprocessor technology